right, the conceptual questions from our Work, Power, and Energy AP1 packet. Let's talk about them. The first question says, compare the kinetic energies of the two balls. Well, the first thing to do is to figure out the kinetic energies. So, kinetic energy is, and if I write, I have kinetic energy is 1/2. Okay, that was weird. So let me see if I can go back down. There we go. There it is. Okay. Kinetic energy is 1/2 mv squared. So for ball 1, we have 1/2 and we have m, but we have 2v squared. So we now would have 1/2 m4v squared. So when we really look at it, we have 4k. And then when we have this one, we have 1/2 and we have 2m v squared. So when we pull that out, that ends up being that this is 2k. So when we look at it, we would have ball 1 to ball 2. So this would be 4 times, ball 1 would be 4 times as much as ball 2. Well, we don't have any of those because the first one says that ball 1 is just the basic kinetic energy and ball 2 is 4 times it. That's not correct. B says that they're equal, which the two kinetic energies are not equal. Now C has that ball 1 has twice the amount of the kinetic energy, which 4k is twice the amount of 2k, so that's a possibility. And then the next one says that ball 1, the ball 2 has twice what ball 1 has. So that wouldn't work because we know it's 4 times. So we would go with C. C would be our answer. All right. So next question. We have a ball with a mass of m1, or box, excuse me, is being pulled up a rough incline by a rope pulley weight system. So by an incline plane on, or by an Atwood's machine on an incline plane. So how many forces are doing work? So we have if we look at the box M1, we have a friction force, and that would be moving a distance, so the friction force does do work. We have a weight force. Well, that weight force would do gravitational work. So we would have, or potential work. So let me erase that. So our F of G does do work. We have our F of N. F of N doesn't do any work. And that would be no work. Oh, hold on, I drew my F of F on the wrong spot. If it's being pulled up the incline. So that would be my F of F is this way, but it still does work. And then this gets my T value, and the T does do work. So I have 3 forces that do work on that particular picture. Okay, because this would do work as negative work. This would do potential energy, and this would do work as well, because we could do the tension times the displacement or the movement. So all of those would be work values. So on number 3, refer to the diagram. A cart starts at a velocity of v and rolls up the path shown. At what point is the kinetic energy greatest? So when we think about it, the kinetic energy should be greatest when the potential energy is the least. So according to, so we have kinetic plus potential equals kinetic plus potential. Always. That's our law of conservation of energy. These are originals. These are our finals. So we want the kinetic energy to be the most, and we want the potential energy to be the least, because kinetic energy has velocity in it. But we just want to double check the kinetic energy is greatest. So that would be at 1, because it has the lowest potential. All the rest of them have some sort of potential energy. Okay? So again, refer to the next diagram, or same diagram. At what point does it have the greatest total energy? Well, according to this, it should always be the same. The law of conservation of energy, there's no non-conservative forces involved, so the great total energy should be the same everywhere. Can the total mechanical energy ever be negative? I would like to add explain on that. So the reason is because I think that you can answer this in a lot of different ways depending on how you look at it, or how you explain it. So my thought would be is, can the total energy be negative? Well, if the kinetic energy is negative, if there's a loss of kinetic energy and there's a loss of potential energy, then yes, the total energy would be negative. So because of either one of those comments that I just made, then that could be true. If the overall energy is decreasing, then you could say yes, but can the total mechanical energy ever be negative? I would say that it could be either B or C, because it could be dependent on the K and the potential energy being negative as well. So I don't know about A, because I don't know that you could always say always, but I do feel like B or C could be a correct answer depending on how you justify. Okay. Number 6. Two forces are applied over a distance of x as shown in the graph. F1 is constant over the distance, but F2 varies from 0 to 2F1, 2 times that of F1. Compare the work done by the two forces. Okay, well, on a force versus displacement graph, I tell you to look at two things. That is the slope and the distance, and the area under the curve. Well, the area under the curve, or the area of this force times displacement graph, is work. So for 1, we have F1 times x, which tells me that the work is F1x. Then for F2, F2 times x, and that's a triangle, so I'm going to do 1/2. Oh, but I was told, hold on, I want to rewrite that, or I'm just going to write underneath it. 1/2, 2f is excuse me, F2 is 2 times F1. So 1/2 times 2 is just F1x. So the work of 1, this is the work of 2. Those look the same. That would mean B is the correct answer. All right. Again, key here was area under the line. All right. Number 7. In the figures below, identical boxes of 10 kilograms moving the same initial velocity to the right. The same magnitude of force is applied, and they go the same distance of d, or no, the distances are not the same. Rank the situations in the work done by the box on the hand causing the force. So really we want to look at the fact that work would be your force times your displacement. So this one would be 5F. This one would be 10F. This one would be 5 cosine theta F. This one would be 0 because the F and the D are perpendicular to each other instead of parallel. This one would be negative 5F. And this one would be 0 because of the fact that they are perpendicular again instead of parallel to each other. So our order would be B, A, C, D is equal to F, and then E because of the negative. So, all right. Then for number 8, our ranking order tasks with the masses, okay, or the cart and the spring plunger. The mass of the cart, its velocity just before impact of the barrier, and its velocity after impact are given in each figure. Rank the work done by the barrier on each cart from the greatest work done to the least work. Positive direction is to the right, negative direction is to the left, with negative 4 being less than negative 2. So we do have to consider negatives. All right. So if we're going to do it by the barrier, then by the barrier is going to be the same as the change in the kinetic energy. So if we're looking for the change in kinetic energy, we have our values as, okay, so we said that the work done by the barrier will be equal to the change in the kinetic energy. Well, when you look at the change in kinetic energies, because it says that negative 4 is less than negative 2, when we figure out all of these by doing our change in kinetic energies values, and we start with our afters minus our befores, we end up with a ranking that should be D is greater than B, which is equal to F, and then we have E, and then we have C, and then we have A. Because A, when you find out the actual change in kinetic energy, should be a negative 80. Whereas when we do our B, it should be a negative 40. And when we do C, it should be a negative 50. And when we do D, it's a negative 20. Oh, hold on. I did those in the wrong spot. No, I didn't. And then E is a negative 47.5 and F is a negative 40. So we have negative 20, and then B and F are negative 40s. And then we have E, which is a negative 47.5. And then we have C is a negative 50, and then this is a negative 80, so it would be the least. Even though it's the greatest change in the kinetic energy because of the comment that's made about the negative and positive and negative 4 being less than negative 2, then we have to set it up that way. Okay? All right, our last one. A rubber ball is held motionless a height of HO above the hard floor and released, assuming that the collision with the floor is elastic, meaning that all of the energy is going to be conserved. All right, which one of the following graphs best shows the relationship, there's the bell in school, between the total energy of the ball and its height above the surface? Well, the key to this question is, yes, it has more potential energy at the beginning, and then it has less kinetic or potential energy when it hits the ground. But this is asking for a graph of total energy, and total energy really should just be that regardless of what height we are, we have the same total energy all the time. And if we have the same total energy all the time, that graph should be E. All right. So you really got to think about the fact of what it's asking you to solve for. Had it been a graph that was looking for my potential energy as the height changed, then B would have been a better one if I was just looking at potential energy, because as I dropped it, okay, then it would be, the height would go, yeah, that's not even a good way of saying it, because that's showing that the potential energy goes down as the height goes up. So no, I don't even like that one. So as the height goes up, the potential energy would go up. That would be better for A. So yeah, A would be a better one if it was just asking about potential energy. So lots of different ways to look at it. But since it's asking for total energy, we want it to be the same the whole time. All good.